Let's summarize the key aspects of this lecture on numerical differentiation. We started out the lecture by stating that analytical differentiation is not always possible, and that based on the form in which the function f is presented to you, whether it's in an analytical form or in an implicit form as the solution of an ordinary differential equation or as a tabulated form, sometimes you can only approximate the derivative of this function f through numerical differentiation. We then proceeded with going back to what's the definition of such a derivative in the form of a limit process, so that we have a infinitesimally small difference in function values divided by an infinitesimally small difference in function inputs. We then proceeded with a intuitive approximation of this formula by not taking infinitesimally small differences, but replacing them with finite but small differences. This also led to the definition of intuitive finite difference schemes, such as the forward, backward, and central difference schemes. And based on a small example, we were able to show that the error between these difference schemes can vary quite wildly. After that, we discussed the approach of Taylor series expansions for constructing finite difference schemes and showed how this allows you to get a structured approach in deriving these schemes, but also allows you to quantify the truncation error that remains after we have done the approximation of the derivative. Afterwards, we discussed Richardson extrapolation, which allows us to easily compute a new and higher order finite difference approximation scheme based on two evaluations of a lower order scheme, and how this can be used to efficiently get a more accurate approximation of a derivative. We closed off the discussion by discussing the numerical errors that are present in numerical differentiation. Based on the earlier discussions in the lecture, one would assume that choosing h to be as small as possible would yield an arbitrarily small error in the approximation of the derivative. However, it's important to note that the total error consists of both a truncation error and a rounding error, which lead to conflicting objectives in choosing the spacing h that you use in your finite differences, and that there is an optimal h, which reduces the error at most, and that higher order schemes can be very useful in attaining high accuracy.